So this is chapter 5, Force and Motion. This is a pretty short chapter. In fact, the main goal of this chapter is to help you understand how to draw a force diagram. We're going to be drawing force diagrams for the rest of the semester. So this is crucial that you understand how to do this. So just put in the effort, make sure you know how to do this. All right, let's see. Objectives. First one, to recognize what does and does not constitute a force. Second one, to identify the specific forces acting on an object. Third, to draw an accurate free body diagram of objects. So Randy Knight says free body diagram. I just call it a force diagram. Same thing. Fourth one, to begin the process of understanding the connection between force and motion. We already talked about that. And then to begin learning how to explain an observation on the basis of physical properties. So we're not going to be solving hardly any problems this chapter. We're just drawing pictures. However, we'll be solving the problems in the next chapter. So if I forget to tell you later on, save all the pictures. So you're going to be drawing a lot of pictures today. Save them, because we'll be solving them next chapter. Okay, so first of all, let's talk about to recognize what does and does not constitute a force. So, what's a force? Okay. All right. So I exerted a force on the whiteboard, correct? My hand hurts. All right. All right. So that I exerted a force, right? Okay, how about this? So pretend there's no air in this room. Okay. So watch me make a fool out of myself. Okay. Did I exert a force on anything? Well, no, because there's nothing here, right? I mean, I didn't touch anything. I mean, if I went like this, I'd be exerting a force on the whiteboard. But if there's nothing, if there's no air, then I'm not exerting a force. So, what's a force? So this is not a technical term or definition, but it's good enough. A force is some kind of interaction between two or more objects. That's the important thing. Two or more objects. When I go like this, my hand is one object, the whiteboard's the other object. When you go like this with no air, the only object is my fist, right? I'm not hitting anything. So that's not a force. Okay, so there you go. So what we're concerned about is what is exerting a force on an object. Okay, so let's do that. Let's do a little demonstration. All right, so let's say Sully is the object. Here's a bungee cord. So I'm pulling the bungee cord. Now, what are the two objects involved? Remember, Sully's the object. What's the other object? It's not me. It's the bungee cord. Because the bungee cord is interacting with Sully, the other object. It's kind of a big deal to identify the objects. I mean, that's crucial when you start drawing force diagrams. Here. So again, a force is an interaction between two or more objects. So here's a force we're going to see the rest of the semester. Weight. Weight is the force of gravity acting on an object. And that's equal to the mass of the object times the acceleration due to gravity. So again, you're going to memorize it. Even if you don't want to, you will, because we're going to use it so often. All right, so weight, force of gravity equals mg. That's what you want to remember. The weight is mg. It's a force. All right, so here is an object, right? First object. And the weight is mg. Now, a force is an interaction between two or more objects. So what's the second object? Well, what's exerting this force of gravity? Earth. So the second object is the Earth, right? The Earth's gravitational force is pulling down on this object. That's all there is to it. All right, here's a neat question. And you might think it's not fair because we're not talking about electricity. We haven't talked about electricity or electric forces. It doesn't matter. Just you know enough to be able to answer this question. A proton is placed at rest at some point A within a room that is otherwise lacking of matter. So just pretend there's nothing in this room except a proton at some position A, wherever that is. At some other point B within the same room, is there an electric force? So pause your videos and figure it out. All right, so I hope you figured it out. Okay, what's a force? It's an interaction between two or more objects. How many objects do we have in this room? One. We have a proton. So therefore, can there be an electric force? No. Okay? A force requires at least two objects, and the room contains only the proton. All right. What's the most important equation in all of classical physics? F equals ma. Right? Ask anybody. Well, most people, and they'll say F equals ma. So force equals mass times acceleration. Acceleration is a vector, force is a vector, mass is a scalar. Now, this is how we usually write it because we're lazy. Or you know, we could just divide by the mass, right? We could divide by the mass. And then we would just have the acceleration equals the force over the mass. But this is just kind of shorthand. What we really, really mean when we write F, we mean the sum of all of the external forces. Okay? So it's we say this is the net external force. Right? So A equals the sum of the net external forces over M. But we're not going to write this all the time. It's too much trouble. So we just write like this. A equals F over M, or you can multiply by M, F equals MA. A is the change in velocity. A lot of people think that A is the change in position. It's not, okay? If the velocity is changing, that means the speed is changing or the direction is changing, it's accelerating, right? So A equals dv dt. Okay, here is a question for you. All right, so what do forces cause? What do forces cause? So pause your video and figure it out. All right, you're back. Well, A equals F over M, or F equals ma. So what do forces cause? Acceleration. What's acceleration? It's, write this like this, right? M dv dt. So forces cause a change in motion, right? dv dt is a change in velocity, a change in motion. So the correct answer is 2. All right, so forces cause changes. That's the important thing. Just, what's a derivative? Change, right? So forces cause changes in motion. So here's an article I read years ago. Well, not an article. This is a letter to the editor in the Honolulu newspaper. Let's read it. And there's a lot of false statements in it, which you should be able to pick up. Bicyclists should be careful on sidewalks. Linda Jackson's February 5th letter cites a difficult problem for bicycles and pedestrians. Unfortunately, there is not enough room for bicycles and pedestrians on the sidewalk, and not enough protection in the streets for the two-wheelers. All right, I don't care about that. This is the part that we care about. Mass times velocity equals force. That means a bicycle traveling 3 or 4 times the speed of a pedestrian carries 3 or 4 times the kinetic energy as the other. A dangerous formula all around. One that calls for a change in lifestyle for some, and I don't think it is legally the responsibility of the walker. I don't know, whatever. Okay, what's wrong? What is this guy? This guy must have flunked high school physics, right? Mass times velocity is force. Is that right? That's totally wrong. Force is mass times acceleration. Now there's something else wrong, but we haven't talked about it yet. So kinetic energy, we'll talk about this later, is 1/2 mv squared. So what does he say? He says a bicycle traveling 3 or 4 times the speed of a pedestrian carries 3 or 4 times the kinetic energy. Totally wrong, because it's v squared, right? So if it's 3 or 4 times, it would be 9 or 16 times the kinetic energy. Okay, so that's very interesting. So don't write a letter to the editor if you don't know what you're talking about. All right, another question for you. Suppose you dropped a bowling ball from a 2nd-story window, and when the ball is about halfway to the ground, somehow the force of gravity suddenly ceases to exist. Describe the motion of the ball after gravity vanishes. Now notice it's only 2nd story, so we're ignoring air resistance. Okay? So this is a good question, so pause your video and figure it out. All right, so you have this ball and it's accelerating, right? A sub y equals minus g equals minus 9.8 meters per second squared. So it's going faster and faster and faster. But then it reaches a situation, or a location, sorry, where all of a sudden a sub y equals 0. So what happens? It just, remember, a is dv dt, right? So it just means that the velocity is no longer changing. So that, whatever speed it has attained here, it just stays with that same speed, right? Because a is 0, so nothing is changing. So let's just say, I'm just making this up, let's say that Vy was minus, 20 meters per second right here, where Ay is 0. That means it's going to stay minus 20 meters per second, right? Because nothing is changing. So the answer is 4. Okay, it stops accelerating because there's no longer force, right? There's no longer force of gravity, so it stops accelerating and then moves with a constant velocity. Constant velocity. Make sure you understand that. Pretty important. All right, another one. Oh, this is a good one. All right, by the way, whenever we talk about deep outer space in Physics 121, we're assuming that it's completely empty. All right, so you can ignore everything. You can ignore friction, you can ignore gravitational forces, just completely empty. Okay. All right, so the force needed to maintain a body at a constant speed in deep outer space, far from all outside influence, is equal to what? So pause your video and figure it out. Okay, so we want to maintain constant speed. Well, if it's constant speed and you're assuming constant direction, because there's no gravity or anything like that, what's the acceleration? 0. And what's Newton's second law? F equals ma. Well, constant speed, we're assuming constant direction, so that means a is 0. So what's the force? 0, right? 0. So, and we talked about this before, right? If you're out in deep outer space and you take something and you throw it, there's no forces acting on it, so it's just going to keep going same speed, same direction forever. Right? Okay, here's Newton's first law. An object at rest will remain at rest, or an object that is moving will continue to move in a straight line with constant speed if and only if the net external force acting on the object is 0. That kind of makes sense, right? I mean, here's a, what do you call this thing? Remote mouse. The net force on it is 0. so it's going to remain at rest, right? It's going to remain at rest. And I just gave that example in deep outer space. If it threw something, no forces acting on it, so it just goes constant speed, constant direction. Let's do something here. Okay, so watch. Okay, so push.
Oh, push. Yeah.
Okay, thank you. All right. So Sally was pushing really hard this way. I was pushing really hard that way. So I mean, there were forces acting on this thing, right? Of course. But yet, Sally was pushing opposite than I was. So what's the net force? 0. So if the net force is 0, the acceleration is 0, and the velocity didn't change at all. So there you go. All right. So that's why we talk about the net external force. Oh yeah, this is an awesome question. A constant force is exerted for a short time interval on a cart that is initially at rest on an air track. Okay, an air track is this long track. It's in the shape of a triangle, and there's all these holes all over the place. And then they push air. They have an air pump connected to it, and so there's all this air coming out of this air track, all these little holes. So this cart just fits on top of it, but the cart never touches the air track because there's all this air coming out of it. So it's supposed to be like frictionless motion, okay? Okay, let me see. So the constant force is exerted for a short time interval on a cart that is initially at rest on an air track. Okay, this force gives the cart a certain final speed. Got it. Suppose we repeat the experiment, but instead of starting from rest, the cart is already moving with a constant speed in the direction of the force at the moment we begin to apply the force. After we exert the same constant force for the same short time interval, that increase in the cart's speed is what? So let me give you a giant hint. That's a V, sorry. Okay, there's your hint. So pause your video and figure it out. Okay, so look, what does it mean? The increase in the speed. Well, you know, the direction is not changing, right? The only thing that's changing is the increase. So that means delta V over, dV dt, correct? So, I mean, the increase in the speed, and then notice it says the same time interval. So, same force, right? Same force, same time interval, same mass. What has to be true about the dV, the increase in speed? It's the same, right? It's the same. Okay? All right? Does that make sense, I hope? Same force, same mass, same time. Oops. So the dV, the change in speed, has to be the same. That's all. Okay, let me give you another example of that. Oops, you didn't see that, right? Okay, I want to give an example now. Well, I want to just describe an example. Okay, so give me a minute. All right, so let's suppose, okay, we're going to drop it, well, this is a free fall example, all right? Free fall example. So A sub y equals minus g, and just to make it easy, we're going to say it's minus 10 meters per second squared, all right? And again, what does that mean? It means minus 10 meters per second every second, right? That's what it means. All right, so let's suppose initially that the object is held at rest. So at time equals 0, the velocity is 0 meters per second. So what is the speed going to be? So then I let go, then I let go. What is the speed after 1 second? Well, minus 10 meters per second, right? Minus 10, because what is this? Again, the acceleration is minus 10 meters per second every second. So if we start at 0, at rest, and then 1 second later, the velocity is minus 10 meters per second. What's the speed going to be after 2 seconds? Well, again, remember, this is delta V over delta T, right? So the velocity is changing by minus 10 meters per second every second. All right? So after another second, this changed by another minus 10, minus 20 meters per second. And so forth and so on, right? 3 seconds, minus 30, so forth and so on. Okay, now, so this was just dropping it from rest. But now, let's change it. Now let's throw it down. Okay, all right, so now, when we start collecting data, when we click our stopwatch, we're throwing it down. And right when we click our stopwatch, the speed of this object is minus 40 meters per second. But we're throwing it, right? So we let go, right? So we let go, and it's going at minus 40 meters per second. So after we let go, it's still free fall, right? It's still free fall. So, what's the speed going to be after 1 second? Well, for free fall, the change in velocity over the change in time is minus 10 meters per second. So what's it going to be? Minus 50. Right? Because it's free fall, so it changes by minus 10 meters per second. What's the speed going to be at 2 seconds? Minus 60. And so forth and so on. So make sure you understand that. It's pretty important. All right. Okay. All right. So yeah, make sure you understand that. That's a good one. This is a good one. Okay. Now we want to kind of shift gears. Now we want to talk about something called a normal force. All right, a normal force, or perpendicular force, or that's good enough. Okay. So here's a question. Here's Newton's second law. F equals ma, right? A equals F over m. Okay. So here I am, standing still. Earth is pulling down on me, right? Earth exerts a gravitational force on me. That's my weight. So Earth is pulling down on me. So according to this equation, if there's a downward force on me, I should be accelerating downward. But obviously I'm not. So why? Why am I not accelerating downward? Well, floor, right? There's a floor there. Okay? There's a floor. So what we say then, we say that the floor is exerting a force on me, which is up. Right? So let's actually draw a force diagram. Nothing very complicated, you'll see. So there's a coordinate axis. You don't have to be an artist, just that's the object, me, right? That's me. What are the forces acting on me? Well, there's weight, which is mg, and then there's this upward force, right? We call it the normal force. Some people call it Fn, some people call it n, some people call it the perpendicular force, because it is perpendicular to the floor, right? So that's a good thing to call it. Whatever you want to call it. But the point is that this force, the magnitude of this force, is equal to the magnitude of that force. So therefore, the net force equals 0. So therefore, the acceleration equals 0. Okay? So that's the normal force. All right. Here's a nice picture. So here you have a box on a table. And so, the Earth is pulling down on the box, and the table is pushing up on the box, because the box is the object. Now, what is this normal force anyway? I mean, really, what is it? Well, what's the table consist of? The table consists of molecules, right? And the molecules are held together with molecular bonds. And we always think of these molecular bonds as like little springs, you know? And so this box is pushing on the springs, right? The box is pushing on the springs. And what do the springs do back? They push up, okay? So that's really what on the molecular level, that's what the normal force is. Now, what if this box were so heavy that it was strong enough to break these molecular bonds? What would happen? Well, the table would break, right? The table would break. Okay, so let me show you some things. Okay, so use your imagination. Oh, one thing I forgot to say, very important. Units. So F equals ma, is magnitude. So mass, the units of magnitude, what did I just say? The units of mass, kilograms. The units of acceleration are meters per second squared. So that means that the units of force are kilograms times meter per second squared. Well, that's too much trouble. And there's all these super important dead people you want to honor, right? So who do you think of when you think of force? Isaac Newton. So this is called a Newton, uppercase N, right? So the unit of force is Newton, right, after Isaac Newton. And again, remember, the weight is the force of gravity acting on the object. That's equal to mg. So it's in newtons, right? So many newtons, you know, because the force is always in newtons. Okay. So just pretend that this object has a weight of 1 Newton. So that means Earth is pulling down on it with a force of 1 Newton. So what is the magnitude of the normal force that this cart surface here is exerting up on this object? Well, what's the acceleration of this thing? 0. So that means that the downward force acting on this has to equal the upward force. So the normal force is 1 Newton. Okay? Just pretend this is a box that has a weight of 20 newtons. So the Earth is pulling down, 20 Newton force. What's the force that this surface is exerting up on it? 20 newtons, right? Because acceleration is 0. Okay, now watch. Now let's say, all right, so remember, the normal force that this object or this surface exerts on this is 20 newtons. Now, let's say I start pulling up on it. What happens to the normal force that this exerts on the box? It gets smaller and smaller. Now let's say I just pull it enough so it's no longer touching. All right, so the box is no longer touching the cart. So what's the normal force that the cart exerts on the box? Well, 0. It's not touching it anymore. Okay. All right. Okay, good place to quit.